Hello dear students, in continuation with my part 1, the design of the T-beam bridge, I am going to continue with this with part 2. In the part 1 we have discussed the design of deck slab. In this part 2 I am going to discuss the design of the cantilever portion, the footpaths as already been mentioned, the longitudinal girders, the cross beams, and the wearing course. The cantilever portion as shown you, I'm going to continue with the same design which we have taken up. This was the earlier design. You can see the data. So these are the three longitudinal girders. They are spaced at 2500 each. This is the intermediate longitudinal girder. These are the end girders, longitudinal girders. This is the longitudinal section where you where this is the this is the cross beams and cross beams. All the other three are the intermediate cross beams, and the fifth one again we have as the end cross beam. This is the longitudinal girder. This is the longitudinal section. So here I am going to discuss you with the design of this cantilever portion. This has been shown in elaborated portion like this. You see over here. So it includes some parts. This is the load which is going to be catered on this cantilever beam is the handrails, the load of the curb, dead load, then the load of this slab, which you can see, which is a trapezoidal section. It has a depth of 100 at the end, free end, and a depth of 350 at the plane of the section, beyond the longitudinal girder and the longitudinal girder. So these are the dead loads. Of course you have a wearing course of 1100 mm. So let us start with the design of the cantilever slab. So as per the portion I have shown you, we are going to calculate the moment due to the dead load, and then we are going to calculate the moment due to the live load. We will combine all these two, and then we will design for the total design moments. So first is the handrails. So it is acting over here. We will make it in a table wise. The description, the load, then the lever arm, then the moment. Combine all the moments, you will get the total moment. Handrails. The load from the handrails has approximately taken up as 1.74 kilonewton. Lever arm will be 1.425. How? It is going to act at the center of here. That makes it to 100, and 50 you have from the edge, so that is 150. So when you subtract from this total distance of 110 plus 475, which makes it to 1575, minus 100 minus 50, it gives me a value of 1.425. That is 1425 units. You can always convert. So when you multiply 1.74 with this 1.425, we get it as 2.480, and so on. We can do the things. Curb size is 0.475 into 0.275 into 0.275 into 25 will give me the, this is the unit weight of concrete, will give me the weight. So that is 3.27. It will act, this load will act at the center, at this center, that is at center of 475 plus 1100. This gives me a distance of 1.34. The moment, this product of these two will give me the moment. Similarly for the wearing course, and then the slab. This slab has been divided into two portions, a uniform thickness of 100, and starting from 0 to 250 the second portion. So you can take their center of gravities, and you can take multiply it with the distances to get the moments. So this total moment, when we calculate, it gives me 13.72 as the dead load moment. Then moment due to the live load. The moment due to the live load, it says we are considering class AA load vehicles, but it says it will not cover the cantilever slab. So here the severe effect is caused by the load of class A. The dispersion load now class A consists of point loads. So point loads, the load of dispersion is given as BE is equals to 1.2x plus BW, where x is the distance of the center of gravity of the load from the cantilever portion, from the plane of the section, from the girder. BW is the load of dispersion. Is here you can see it is D plus 2H. D is the thickness of the slab, H is the thickness of the wearing course. So this gives me 0.4. When you substitute these values, now x values is 0.7. So this x value is from here. This is the load position, and now I need to show you the load also. So when you see the load. This is class A vehicle load. So this load has a width of, here this is W, has a width of 500. We have taken 57. This is the most severe load. This is 114 is the XL load. Consists of two tires. One tire will give me the value as 57 kilonewton, which has a B value of 250 and W value of 500. So you can see over here. So it has to be placed at a clearance of F. So F is 150.15 meters from the, it is shown here from the curb. So in this case, the placement of the load is something like this. So it is 150 over here and 500 is the width. It is going to act over here. This distance is X is point 700. These all mentioned in the figure distances are in mm. So please note. So this gives me BE as the load of dispersion, width of the dispersion as 1.24 meters. Live load per meter width will be, including impact, will be 57 divided by the width into the impact factor. So 1.5 has been taken as the impact factor. So maximum moment will be, so the load that is 68.95 kilonewton into 0.7. So that gives me live load moment as 48.26 kilonewton meters. Combining these two, I will get the design moments. So dead load moment plus live load moment, it is 61.98, approximately taken to 62 kilonewton meters. This you know how to calculate the effective depth required, m by r under the root. So this gives me 237.41 as the required depth. The depth provided is, I have told you we have provided 350. So 350 has been taken as the depth provided at the maximum moment where the place is, where the moment is maximum. So 350 minus cover minus half the diameter of the bar we are going to use. We are going to use 16 mm dia bars. So minus 8 gives me 302, which is being provided. So provided is more than required, hence we are safe with. So we can design the reinforcement. Reinforcement is M by sigma st J into D. Sigma st is the permissible stress in steel, that is 200. J is 0.9. Then we get this steel as 1140.32 mm square. Providing 16 mm dia bars at the rate 220 mm center to center plus 12 mm bars at the rate 220 mm center to center. With this gives us total steel as 1428 mm square. Then the distribution steel has to be provided. The distribution steel, the bridge code says it has to be designed for 20% dead load moment and 30% for the live load moment. So this gives you a moment of 17.22 kilonewton. On the same basis, I give the distribution steel. Here 10 mm die has to be provided. So D, my effective D comes out to be 350 minus 40 cover minus the die of the main bar minus half the die of the distribution steel. So this gives me 289 mm. So this has to be used over here. So this gives me, provide 10 mm bars at the rate 220 mm center to center, which gives me an area of 357 mm square, which you can check your calculations. So this is the design of the cantilever slab. Then next topic is we are going to discuss the design of the intermediate longitudinal girder. The intermediate longitudinal girder, as you can see in the effective span, is 14.5 meters. Then the slab thickness is 215 meters. So we will go to the picture again. You can see the data over here. Let me show you very clearly. So this is the data for which we are going to design. The slab thickness is 215. The longitudinal girder has a depth of 1575. So this is incorrectly shown over here. The depth of the longitudinal girder is 1575. So let me show you. So here is the overall depth of the beam is 1575 mm. So it will be shown in the subsequent figures also. Okay, so let's come back. Then we are going to design the longitudinal girder. Longitudinal girder, again we have to, as we have done in the case of this cantilever beam, we have find out the bending moment due to the dead load and then due to the live load. So first here dead load will be checked. So dead load consists of, for the longitudinal girder, the wearing course, the deck slab, the T-rib and the fillets. T-rib width has been given to us as 300 mm. The spacing of the main beams is 2500, this we know. So wearing course is covered for 2.5 into 2.075 into unit weight of concrete. 2.5 is the spacing of the main beams. So this gives me 4.86875. Similarly, you can go for the deck slab. Deck slab thickness is 215. So it is for 2.5 into 0.1 into 25. Then the T-rib. T-rib, you have a thickness of 0.3. For the T-rib, the thickness is 0.3. Then 1.35 is your, you can say, depth of the T-rib. Then into 25 has been taken. So from 175 you can just subtract 215 and you'll get it approximately as 135. It is 136 rather, to let it be 1.35, no problems. So into 25, so this gives me 10.125. Fillets are these are the fillets. So there are two fillets in the intermediate longitudinal girder of size of 300 and 150. So it will be 2 into 0.5, 1 by 2 triangular hai, into 0.3 into 0.15 into 25. So this gives me this value. Cross beams, it says the load of the cross beams, the total length has been taken. When you go through the longitudinal section, from center to center, from this center, this is 7.25 half section, into 2 will give me 14.5, which is the my span of the longitudinal girder. So like we have a distance of 300 on either side, in one this side and one on that side has to be included. So this gives me total span of 14.5 plus 300 plus 300, that is 15.1. So this is 15.1. So 5 cross beams of 2.2 into, this is the depth of the cross beam, into thickness of the cross beam, into 25. So this gives me total. So this 34.211 is the total UDL which is going to come on the longitudinal girder through dead load. So if you want to take out the moment, this moment is given by WL square by 8. So W is 34.2 and L is 14.5. So this gives me 14.5 square by 8. So the moment comes out to be 898.82 kilonewton meters. Then bending moment due to live load. For bending moment due to live load, the severe effect comes out from the class A 2 lane loading. For that, impact factor has been calculated as 4.56 plus 14.5, that is 0.22. The loading has been arranged. I'll show you how the loading has been arranged. Now this is the loading. So this is the load W, and W. These are the load from the cross beam. So these are the longitudinal girders 1, 2 and 3. Let it be A, B and C. So we are going to find out some reaction coefficients for these. So this is the placement of the loading in the transverse direction. So when you see class AA loading, the I'll let you again show you the class AA loading, how it has been placed. So for the class AA loading, then again we will see that let me show you the class A loading. Anyways, so I'll show you in the so class A loading. When you see that you have already with you the class A loading, so you see it has a this clearance factor of 150, and then it starts, it is the center line where you have a width of 250. So this distance is 400. I repeat, clearance is 150, then width of the this tire is 500. So that is why it has been taken as 500. The severe case has been taken up, so that is why you're getting this as 400, this distance. This is the line diagram, and there you have the width as 500, so half the width has been included in here, so this is 400. Then again center to center it is 1800, 1700, 1800 and 1800. So this way you have this as the W as the loads. So these are the severe loads. Now for live load bending moments, there are four methods: Carbon's method, Henry Jaggers method and Morris Little method. So we will be calculating from for all these three methods, and then whatever the critical one will be covered, will be taken up as the live load bending moment. So we'll start with the first one, Carbon's method. This method is applicable for the ratio of the for the some conditions. The first condition is the ratio of span to width is greater than 2 but less than 4. The longitudinal beams are interconnected by symmetrically spaced girders of adequate stiffness. The cross girders extend to a depth of at least 0.75 of the depth of the longitudinal girder. It says that the T-beam girders, wherever you want to design it, these covers all these points. Hence, Carbon's method can be applied to T-beam girders. So here a reaction is given to you on your screen. You can see that it is P into I divided by sigma I, sum of i's, plus Pi into I, again divided by summation of i's, into E into Di into summation of i's, then summation of I d square I square. Simplified equation give us in this format. So this is one. Let me explain you. P is the total live load. I is the moment of inertia of longitudinal girder, which is being considered. E is the eccentricity of the live load. Then Di is the distance of the girder I from the axis of the bridge. So if you look at these three girders, this is A, B and C. So if I'm going to consider this central, we are going to design the intermediate girder. So when I'm going to consider this, so this distance is my Di. So 20 Di is 2500. Then W is your load, so it is 1 2 3 4. So it is 4. W is my P. N is 3, so summation of i's will be 3i, and hence an E is the eccentricity of this load where it is going to place. It is, you can say, 700 from this central girder. So that means the CG of the load is somewhere at a distance of zero point 0.7 from, this is the CG of the loads. So it is at an eccentricity of 0.7 from the central axis of the bridge. So when you substitute this, you get the value of Ra, which comes out to be 1.89 W. Similarly, we can substitute for Rb. Okay, let me substitute the values. So P is 4W, I is I for Ra, then 3I, then 1 plus, I'm substituting the equation, 3I, 2I d square, I have told you, into 0.7, this gives me 1.89. When you go for Rb, then Di is 0, when this is into considered, Di is 0, therefore Rb comes out to be 1.33 W. Total is 4W, subtract 1.89, yani Ra and Rb, and you get Rc. So this comes out to be 0.78 W. Now this figure is the arrangement of the V loads in the longitudinal direction for the maximum moments. So the class A loading has to be arranged on this. Now what is this? This is the section, this is the, you can say, line diagram of the longitudinal girder. This Ra and Rb are not longitudinal girders but the reactions from the longitudinal girders. So you are going to look now in the longitudinal direction. So here this is the class A loading. First load is of 13.5 kilonewton. Here some value is different. I'll tell you how to get this value. So when you look at class A loading in your design diagrams, so it is 13.5, then 13.5, rather it is 27 over there for XL load. So when you half it, it comes out to be 13.5, 13.5, then 57, 57, and then you have this as 55. I don't remember this. So you can just go through that loading. So this gives me now how to calculate. So this, we have calculated one reaction factor, that is 1.33, and we have also calculated the impact factor. So the impact factor has to be taken into account. So this gives me, for the first value, let it be 13.5, and then 13.5, this is for 68 kilonewtons, the loads. Though I told you this is 13.5, so first load is calculated like it is 27 by 2 into the reaction component, you have calculated over here 1.33, then into 1.22. So when you do this, it comes up to 21.9 kilonewton. So my load here will be 21.9 kilonewton. So first one, second one, this was 114. So 114, that is by 2, which gives me 57. Let me do the calculations also for you. One calculation I'm going to do for you. I hope it is clear. So 114 divided by 2, that is 57 per wheel load. into 1.33 into 1.22. So this gives me a load of 92.48 respectively, and I have taken it as 92.5. So likewise you can calculate the load. The placement of this load is such that this will give the maximum moment. Now you see that the maximum load is 92.5. So my two central middle zone, one third zone in the central beam, it has consists of the maximum moments. So this load has been so arranged that this distances are arranged. These distances are fixed. The in between the loads distances are fixed as shown in the class A or B loading. This distance has to be arranged. I mean, I need to place my first load somewhere so that I get maximum moment around this zone. So this is the, you can say, influence line diagram will help me to achieve this. So beyond this, now these are the calculations which can be done. So considering as the line diagram as you have been doing earlier on, so I can calculate RA and RB, the total loads. Then I can calculate the value of RA and RB over here, I mean the reactions. This will give me the maximum moment. So this comes out to be 750.551 kilonewton. This is under the fourth load. So the fourth load over here under this, that is 92.5, considering all the loads over left of the section, gives me the maximum moment as 750.51 kilonewton meters from this Carbon's method. So this is one method. Then we have second method where there are three equations as you see in your picture. A is 12 under the divided by pi raised to power 4 L by H whole cube, and N into E into I T divided by I E I. I T is the moment of inertia of the cross beam, I is the moment of inertia of the longitudinal beam, L is the span, H is the height of the L is the total span, H is the span, this longitudinal, the spacing of the longitudinal beam. You can see that. So L is the span of the girder, H is the spacing of the longitudinal girder, N is the number of cross beams, EI for longitudinal girders, EI1 again for the inner, then EIT is the for the cross beam. So I have drawn you the sections over here. From here you can calculate the moment of inertia for the two sections. When you substitute into the A, you get this value as 50, approximately 48.68, which I have taken as 50. There are four curves, B1, B2, B3, B1, B2, B3, B4. B1, B2 corresponds to F value, this equation, F value as 0, and B3 and B4 corresponds to F value as infinite. It says the distribution coefficients. So these curves which I'm talking about, let me show you the curves also. These curves gives me the distribution coefficients to be calculated. Look at this. So I have some coefficients M11, M21, M31 against the parameter A. So for a value of parameter, you need to find out these three coefficients. These are called the distribution coefficients, and distribution coefficients are to be arranged in such a fashion. It is in the form of a matrix form: M11, M12, M13, M21, M22, M23, M31, M32, M33. This you all know. It is a 3 by 3 matrix and has to be arranged. So let me find out. So against 50, now the T beam has to be designed for a value of F infinite. So first I'm going to look for the distribution coefficients for 3 girder bridge with load on girder number 1 with F as infinite. So corresponding to 50 value, this value comes out to be yani M11, it is 0.4. So I'm going to fill in this table of 0.4 for girder A when load on girder A. So it's 0.4. Similarly for M21 and M3 against 50, I get this value as 28.28. So I've taken M21 as 0.28, but for little calculations I've taken this as 0.32. So I have filled these three values. Then I go to curve number B4. So B4 gives me values of M22 and M12 against corresponding to 50. So this is 20, 30, 40, and this is 50. Corresponding to 50, when I see this gives me an approximate value of 0.34 and 0.32. So M22 is 0.34 and M12 is 0.32. So M12 over here it is 0.32. Now these are the coefficients. The sum of the coefficients will be 1. So this is 0.4 plus 0.32 makes it to 0.72, minus from 1 you get it as 0.28. So all these three can be filled. This way the sum will be 1, this way sum will be 1. So column wise you have the coefficients, the sum as 1 for girder A, girder B, girder C as well. This also, so I can find out the other values. So this way I have founded the values. Now the load diagram, I go back to the load diagram again. So this is my load diagram. So corresponding to this load diagram, this one, corresponding to this load diagram, I need to find out the reaction components A, B and C. Now for the Henry Jagan methods, it says when you solve this, now this becomes a simple continuous beam where I have point loads. This is the overhang, this is one continuous beam, this is the other beam, again this is an overhang. So I have one load on the overhang, one load on the continuous beam, point load, and 2 point loads on the other continuous beam. So I can solve this by either of the methods. I have some methods, that is moment distribution method or conjugate beam method. So I can solve for the reactions RA, RB and RC. So when we solve that, the moments comes out to be MA, it comes out to minus 0.85 W, minus 0.19 W at the central support and 0 at the third support. So corresponding to that, I get my reactions as RA as 1.884 W, RB as 1.352 W, and RC as 0.764 W. Now using these coefficients and these reaction components, I'm going to find out the reactions at the girder A, girder B and girder C, because this was for the unit loads. These are the distribution coefficients for unit load on girder A, for unit load on girder B, for unit load on girder C. So I have now the values of the loads. So on for this 1884, so when 1.884 is multiplied by 0.4, so this gives me component of 0.74754 W. Hence I'm going to find the components for all these coefficients. So 0.32 into 1.884 will give me 0.062 and so on. So I can find out the distribution loads on girder A, girder B and girder C. So this I will do for all the reaction components. Then I will add on these and my net reaction comes out to be 1.38 W, 1.322 W, 1.302 W for girder A, B, C respectively. So these I have to be used further on. Then my design bending moment, which I had calculated in the carbons method, was I got it as 750.51. So you can see over here. From carbons method, the moment came out to be 750.51. So this was corresponding to a value of 1.33. There the reaction was, central girder was 1.33. So here I have a reaction of at the central girder reaction is 1.322. So correspondingly I am going to find out the design bending moment. So I get the design bending moment as 746 because the loading is same, so it is 746 kilonewton meters. So I have taken this moment comparable and I have taken this corresponding to 750 kilonewton meters, combining this with the dead load moment. So I get my design moment as 1650. Now the effective flange width is given by thickness of the web in plus 0.2 into 0.7 of the effective span. This gives me a flange thickness of 2.33 meters. So effective depth will be 1575 minus 120 minus 120. From the top 120 allowance has been taken and from the compression again 120 has been taken. So effective depth comes out to be 1335. So 1650 into 10. AST can be calculated again in the same fashion. AST is M by sigma ST into J into D. So this is the steel. So I have provided 12 bars of 28 mm dia in 3 rows of 4 each, which gives me provided steel as 17389 mm square. For shear I have provided 4 legged stirrups at the rate 10 mm at the rate 120 mm center to center. So this was the design of the intermediate longitudinal girders. Then we have the design of end longitudinal girders. The end longitudinal girders can be designed as similarly with the intermediate longitudinal girder as per the design of that. Here bending moment due to dead load was 898.82, so that has been taken up. Then the reaction water from the Henry jagged, I have got it as 1.4, so I have used that 1.4. It was now in this case Henry jagged it was 1.38 rather. So I have taken 1.38, which gives me a values of 70 and 90 kilonewtons. For end longitudinal girders, only difference is that 10% movement has been increased, so 10% gives me 869 ahead of 790. So total design moment comes out to be 176.7. You can increase in the end intermediate longitudinal girders. We have provided 12 bars. In the end longitudinal girders, we are going to provide something steel more bars, that is 14 bars at the rate for 28 diameter. Only difference is that steel has increased, rest design is same. 862 square is the steel provided for the end longitudinal girders. So here I stop with the design. Part 3 will cover in design of the intermediate cross beams and the end cross beams. Thank you.